And this is just very exciting to me to get to talk to teachers. My sister and brother-in-law are both high school teachers, and I can tell you honestly that is something I probably could never do. Just having to talk all day would be really hard for me. Can you guys tell me what take-home messages you got this morning about batteries, in particular for cars, so I can decide which parts of my talk I should emphasize?
Yes.
Oh, you're whipping out notes.
We specifically talked about that shape diagram there.
Yeah.
Between energy, the size of the electrodes, for power, the surface area, for
Perfect.
amperage.
Oh, perfect. That's perfect. Okay, I will show you pictures that look a little bit about this. I will explain that, yeah. What else did you learn about?
I have it right here.
All notes. That's great.
Kind of in general, battery life, factors.
Okay. Oh, good. And what did
Affecting state of charge, things like that.
and what did Tom say about battery life for cars? Did he say what the ideal is or what people are working toward?
I'm sorry.
Did he say what the ideal was or what goals?
3,000 hours.
3,000 hours. Okay.
Was the target number, I believe it was.
3,000 cycles.
Or, I'm sorry, 3,000 cycles.
We talked about
Cycles. Okay, perfect.
Cycle life,
Mm-hmm.
Right.
efficiency, amount in, amount out,
Good.
power and energy densities.
And did you talk about lithium-ion batteries in particular, or did you talk about all in general?
Lithium
Lead
ion.
acid, lithium ion.
Oh, good.
lithium
Okay.
hydrate.
Great.
Well, one thing that hasn't really been talked about is battery temperature.
Oh, okay.
Stabilization.
Okay.
That hasn't really been discussed at all.
Perfect.
But it is a kind of a problem in the industry.
It's a big problem, yeah. Yeah, okay, that's great. So I guessed kind of right. So I'm a chemist, and my passion is figuring out new ways to make things. So it's a lot like cooking. For any of you who like cooking, it's almost exactly the same. I tend to choose problems where people sort of in theory know what the solution should be, whether it's a better device or a certain kind of physics model they're trying to test, but nobody has been able to make the right compounds or make the compounds in the right shape, and that's what I like to work on. So batteries is a big part of my research group. We also work on solar cells and on hydrogen storage, but all of it has a basic synthesis component. So I will get to that. But did Tom tell you what the first battery was? This, okay, cool. Good, good. So this is arguably what for a long time people have believed to be the first battery. It was not rechargeable, but it's a huge stack. This is called the Volta pile, and it was developed by Alessandro Volta in about 1800. And I think the best part of the story is that it came out of an argument with a very good friend of his, a guy that was named Galvani. You may have heard of galvanic cell. And the point was that Galvani was studying frog legs, and he figured out that if you detach the legs from the poor frog and you hook it up to two different metals, a lot like the kits that you're using here, you could make the legs jump. And they were arguing about why that was. And so Volta's contribution was to say, well, you don't actually need the frog legs. The only important part is the salt water that's in the legs. And so he decided to try to show the same kind of behavior, not the jumping, but the electrical current. And the way he did it was he stacked really thick copper and zinc plates separated by cardboard that were soaked in brine. And that was the first battery. It was about a 1.4 volt battery.
Let me ask you about going farther back in history. Baghdad battery.
That's this one. That's right. So people thought this was the first battery. This, I think, is the first battery, although archaeologists are still arguing about it. But it is exactly the same thing. It's a clay jar, exactly the same. Copper and another metal, and they use very different metals. In some cases, they found zinc, and in some cases, they've found alloys that are close to brass. They always find residue of either lemon juice or wine, and that would have been a 0.78 volt battery. So, and there are even examples later in history of similar things in Egypt that they think were used for plating jewelry. So, still a battery, I think. It's a very similar concept, but yeah. So I would argue the first battery probably is the Baghdad pile.
How did that convert into the Daniel cell? Or
further optimization, trying to get bigger voltages, and trying to play with different metals.
Okay.
Now, in terms of teachings, when I talk to the general public, in particular people who don't maybe think about science in everyday life. The reason I love this story with Volta is because he and Galvani were very close friends, but their arguments apparently were spectacular, with some pretty heated, very crass language, I would say. It's pretty insulting language. But what came after this Volta pile was the cell that Volta did come up with, but he named it the Galvani cell after his friend, out of respect for the ideas. And so it was through that, and then Daniel came a little bit after, and they came up with the Daniel cell also. So batteries have been around for a long time. Ours don't look like that anymore. This is why we care about, in particular, lithium. So for almost every application you can think of today, there is a battery associated with it. And I'm showing you sort of the common ones: laptops, phones, tablets now on the right. I'm going to be focusing on the Tesla Roadster in a minute because I think it's the most beautiful example of a battery-powered application. But there are also, you can imagine, examples for grid stabilization and for energy storage as a result of either wind power or solar energy. So we have a lot of applications like wind and solar where the energy isn't produced 24 hours a day, 7 days a week, but we don't have any good way to store it. So when the sun goes down, we don't really do anything with our solar cells because we don't have good ways to store energy quickly. So I'll come back to this idea, but in particular, let's talk about the Tesla Roadster in a minute. Now, my perspective is very, very different than Tom. So he's an engineer. And so he has a much better understanding of the whole system application of it. As a chemist, what I was thinking about when I saw this car was the fact that it's so fast. Many people have the misconception that electric vehicles can't be fast, and that's not true. What it does require is a battery that will discharge very quickly, and that's what I call power density. And that's what you guys were talking about with these different shapes. Now, the other key is that it does go 244 miles on a single charge, but I put that in quotes because that's when it's new. It's just like your cell phone. The longer you use it, the less capacity is available to you in the battery, and I'm going to explain to you the chemical reason for that in a little bit. But the kicker to me is the cost, the replacement cost. So this battery, now you can get warranties, and they will buy back batteries after a longer period of time, but in the original Roadsters, the batteries had to be replaced every 2 to 3 years. And that also depended heavily on how you drive the car. So you can imagine the kind of people who buy a sports car like this are probably not gentle drivers. And so the faster you accelerate, and the more times you do that, the shorter the cycle life is on this car.
So we were talking yesterday about the battery options, and
Yeah.
there's, correct me if I'm wrong, like 45, 65, and 85 kilowatt hours.
Yeah.
Which one is that $36,000?
This is the 45 kilowatt hour battery. Yeah.
Okay, so
Yeah. And even the Chevy Volt, which is so this car is 150,000 new. The Chevy Volt is being sold at a loss, in large part because of the battery pack. So what I was thinking about was, what if you could build a battery that would charge and discharge really fast? Because that's really what you need, not just for acceleration like this, but if you think about regenerative braking, every time you take your foot off the accelerator, the brakes try to transfer the power back into the battery, and most batteries can't absorb that very efficiently. So if we could make one that charged faster, that would be good. It would also, for applications like phones and laptops, make people use their phones in a very different way. So imagine if you could take your smartphone and charge it in 5 minutes instead of a couple of hours. Then you wouldn't have to worry about watching a video, using your GPS, all those functions at the same time. And in particular, what I was really thinking about was large-scale grid storage. So I have my solar cells absorbing sunlight all day, transferring the power that's not being used immediately to a battery pack. And then at night, you could use that power, but more importantly, say you're plugged into a typical electric grid like what Fort Collins is on. What happens is there are fluctuations in the grid power that need to be stabilized. And the only way to really do that with a battery is to have a battery that can discharge really quickly in rapid response. So batteries aren't really very good at that. So I was thinking about that, but this number, this $36,000, was pretty horrifying to me. So my thought was, if we could come up with not just a great battery, but try to think of a way to do it in a really cheap way so that everybody could use it, we could drive down that cost. So let me talk about how, as a chemist, I look at batteries. Now, this is a lithium-ion battery with just cartoons. On the left, I'm showing you the positive electrode, the cathode, and that's usually something like cobalt oxide. And then on the right, I'm showing you the negative electrode or the anode, and in all your phones and laptops, that's graphite. And structurally, the way a solid state chemist looks at this, graphite is just layers. It's just like stacks of paper. And the lithium ions go between the layers. And they are formally lithium zero. So the electrons get donated to the graphite sheets. Any of you chemistry teachers that have ever put lithium, I don't even know if you're allowed to do this in high schools anymore, put lithium or sodium metal in water. Okay, so you know.
Never 5 grams, so.
Oh, that's a pretty good fire. 5 grams. Okay.
Well, but you never use that much. I mean,
Right.
yeah.
That's right.
Yes, we do.
That would. It's a big fire. So
Yeah.
that's part of the problem. You guys have already talked about probably with batteries. So it's lithium, formally zero. You know the lithium wants to give up its electron. So what happens is when you hook this up, the current goes through the circuit to do work. And what's really important from a chemistry perspective is that the electron gets dumped in this metal oxide. And you go from cobalt 4 plus to cobalt 3 plus. And so the lithium ions have to diffuse all the way across. They have to work their way into the structure to make it charge neutral. So a couple of things happen there. One, you're taking an electrode. Every time you put lithium into it, it has to expand in volume, and every time you take lithium out, it contracts. So over time, your electrodes pulverize themselves. So if you notice that your cell phone is not keeping good charge anymore, there's no chemical degradation that's really happened. It's that your electrodes have pulverized themselves, so they're not in good electrical contact anymore. So you're carrying around all this weight that you're not using. That's part of why batteries are never discharged all the way and charged all the way. If you stay kind of in a narrow range, this volume expansion isn't as bad. And then the other problem is once the lithium ions get to the surface of this electrode, more lithium can't come in until the first guys get to the middle. And we call that solid state diffusion. It's really slow, especially at room temperature, it's really slow. People have figured out if you take those electrodes and make them very high surface area, this volume expansion isn't as bad, and the lithium ions don't have as far to go. So that piece of it will make the battery charge faster, and that's what this does. You're just making more surface area, less bulk. But the problem is you still have this diffusion from this side to this side. So that problem nobody's solved yet. If you can imagine making really high surface area electrodes, but now you want to fit them into each other so that they're close all the time, then you could get a battery that would charge and discharge really fast. So in this cartoon, what you want to do is bring these two together so that all the grooves fit. So nobody's been able to solve that, so that's what we decided we wanted to work on. So what we decided to do was think about how normal batteries are made. You might have seen something like this morning, but basically all of those batteries that I'm showing you are all sheets. And they're pretty thick sheets, and they get stacked or rolled, but we're going to call this a two-dimensional battery. So because the sheets are so thick, you don't get the fast charge and discharge, and it has a lot of pieces that have to be assembled. So this is what we decided to do. We decided to think about a very different kind of a battery. On the top, I'm showing you just a normal battery. And then on the bottom, I'm showing you what we're trying to build. And I do have a startup company that's working on this. So my academic research group works on some of the basic chemistry behind it. And then I have a company that's actually trying to commercialize it and scale it up so we can try to give it to people to test it. But here's the ultimate take-home message. If you don't get anything else out from the rest of my talk, normal batteries, like for a smartphone, take about 2 hours to fully charge. And they last about 7 hours depending on how you use them. They are made of multiple sheets that get stacked. And what that means is that the ions really can only flow one way. It's because they can only go from one layer to the next. The other key piece is they have some toxic chemicals associated with them. In particular, the liquid electrolyte that normal batteries use are really flammable. So the problem with lithium-ion batteries is once they catch on fire, you have a flammable solvent that helps the fire go. And then as the cathode decomposes, it generates oxygen. So you have a flame with an oxygen source right next to it. So we wanted to get rid of that. In our case, what we do is we build a battery out of a single piece, and I'll show you step by step in a few slides. It charges, in theory, 5 minutes. Our battery, so far, is exactly backwards from most. Ours works a lot better if you heat it, and I'll explain why that is. But our batteries work the best if we put them in about 100 degrees Celsius oven. And they're really safe, they're very stable, there's nothing flammable, but they don't work very well at room temperature yet. But our calculations say they should be able to fully charge in 5 minutes. They should last 10 hours if you use it the same way as this. And that's because of how we make it, not because of the materials themselves, but because of how we assemble them. It is a three-dimensional structure where everything is layered on top of itself, and so you get multi-directional flow for the ions, and it is made all out of a single piece. Now, remember I told you my real goal was that if this was going to ever be useful, it had to be cheap. So the way we started thinking about this was we made a list of everything we were not allowed to use. So we weren't allowed to use any expensive equipment, nothing that required high temperatures, nothing that required a clean room, nothing that required vacuum deposition chambers. So once we got rid of all of those possibilities, what we were left with really was electroplating, which we think is the best way to do this. It's never been used for batteries before, but it's really well-known technique for plating nice jewelry, car bumpers, but also the semiconductor industry uses it a lot. It's very scalable and it can be really cheap. And then again, as a chemist, thinking about if this ever works, imagining a plant based off this idea, we didn't want there to be any toxic chemicals. So we have tried to design all the chemistry so that it happens out of water, that you can just do on a bench top. And we've eliminated the liquid electrolyte, and more importantly, we eliminated one of the salts that they put in the liquid electrolyte, which if you were to crack open a battery and expose it to air and water, that salt decomposes to generate hydrofluoric acid, which is incredibly toxic to humans. So there are many states now actually where if you get in a car in an electric vehicle, EMTs are not supposed to try to get you out. They're supposed to wait for a hazmat team to come. And that just seems ridiculous. So we're trying to figure out a way to get rid of that. Okay, so this is the goal. Now these are just calculated numbers. This is what our model says should happen. I'm going to show you real data in a while so you can see how we think about this process and how we measure what we're actually getting. And then I'll show you where we really are. But we should get very high power density. And the calculation says up to 1,000 times improvement compared to the batteries you guys have in your devices. Now, that assumes there's no loss, there's no resistance, extra resistances that occur, so that won't happen. But it very conservatively could be 10 to 100 times better than a current battery. And that would be good enough for lots of applications. Because of how we make it, we get about 2/3 the size of the battery for the same energy. So you could think about that two ways. One, make a smaller battery that lasts as long, or make the same size battery, but your car could drive further. We are aiming for greater than 5,000 cycles, and I will show you that. I'll show you a set of data where we cycled our battery versus a regular phone battery, and you'll see how much better ours does at high speeds. And then again, we got rid of the liquid electrolyte, and we don't have any HF acid production. The battery manufacturing process is traditional electroplating. So again, never been used in the battery industry, but it is very well known in lots of other industries. So we basically have built a little pilot line where we have our electroplating process and then kind of state-of-the-art battery packaging at the back end. It's all water-based and it is actually repeatable and scalable. We've proven that. And so then this comes to the cost. Okay, current lithium-ion batteries are compared in terms of units of dollars per kilowatt hour. Did you guys talk about that at all today?
You said 50 to 500.
That's for all battery chemistries. Yep, so lead acid batteries are in the 50 range. $500 is if you buy it from China. There's a very good fully integrated company that builds their own batteries and their own cars, combine them. They're called Build Your Dream, BYD. They are about $500. The only American company that falls in this range is A123, and they make their batteries for about $1,200 per kilowatt hour. They sell them for about $800 per kilowatt hour, and they apparently are going bankrupt in October, which makes sense if you think about that kind of math. So the goal is to get, obviously, to there. Our Department of Energy has set a cost goal of $250 per kilowatt hour if electric vehicles are going to be commercially viable. So if we calculate the way we make our battery, all the chemicals that we use, and the time for each step, plus all the equipment, we get a number right now of about $348 per kilowatt hour. But we have some good ways to drop that. And so that doesn't include bulk chemical pricing. It doesn't include very large scale. So I think that if our battery ever works as well as we think it will be commercially competitive, which was my personal goal. Okay, so, yeah.
That price, is that strictly direct labor, direct material, or does that include the infrastructure
It includes the infrastructure.
So that's a complete unit cost. I mean,
That's right.
cost of goods sold.
That's right.
Okay.
That is right. What it does not include is everything you would have to build around it to put it into the car. So the heat management.
What
Yep.
solar calls balance of plant.
That's right.
Okay.
That's right. But these numbers, I did compare apples to apples. So these are what are called cell prices, and ours is a cell price. That's right. Those are great questions. We also actually did include like the cost of the power to a plant. So we did try to be very realistic, and we did include a cost for like chemical waste disposal and water recycling. But we estimate, because we don't have a big plant yet, we estimated that based off known plants that aren't used for battery industry but are used for electroplaters.
And there begins the differential between manufacturing in the United States and being offshore.
That's right.
In my mind. Sorry.
That's right. That is correct. Okay. So first look at this plot. You might have seen this morning, or a version of this. So battery people typically think about watts per mass or kilograms. And so here I'm showing you power density, watts per kilogram, energy density, watt hours per gram, or kilogram, excuse me. And remember, power density is how fast you get power in and out. Energy density is how long you could drive the car. And I'm showing you lots of different chemistries. You have lead acid batteries here, nickel metal hydride, like what you have in the Prius. This is the Prius cell. The A123, the American company I talked about, their claim to fame was very high power density. I am showing you, excuse me, something that's not a battery. It's an ultracapacitor. Ultracapacitors charge and discharge very quickly, but they don't store power in the bulk of the material. It's all charge stored on the surface. So they have very low energy density, but they're very fast. So there are hybrid vehicles now that couple a battery with a capacitor. And then this new pack, it has been tested by a third party, but it is not yet sold, from a company called Envia. And they came up with a new cathode material that gives them very high energy density. So this is where they are. And then what we did is we took what our calculated performance should be, and then we cut it by 50%, and that's where we fall there. So this is mass. But there are many applications now where people don't care about mass, they care about volume. So for example, cars, that's more important. Large-scale grid storage, that's more important. So you don't care how much it weighs because it's going to be stationary, but you do care the total volume. If now I plot this all in terms of volume, I saw power density in kilowatts per liter, and we had to switch to kilowatts instead of watts because we are so far off scale, and then energy density in watt hours per liter. And now you see where the real benefit of the architecture that we're trying to build is. We get this power density for two reasons. One, we use an anode material that stores a lot more lithium per unit volume than graphite does. It's also a lot safer. But also, because we electroplate, we don't have to add all these binders and excess mass that batteries typically use. And so we've gotten rid of a lot of the inactive mass that doesn't store lithium anyway. And so we can store a lot per unit volume. So the energy density is still not close to this company. They have a very exciting result. But the power density is kind of off scale. So we tend to talk in terms of volume, not mass. Okay, so this is how we make our battery. We start with a copper foam, and this stuff's really beautiful. It looks like a copper sponge. You can see through it. It's really light. It's 98% air, and it is a lot less copper than what you typically use in a normal phone or laptop. We use this as the electrode to do an electrochemical plating or electrodeposition, and we plate our anode material. And I'll tell you a lot more about what the anode is in a minute. It is actually purple. That's why I'm showing you as purple. And then we take this, the anode we use is a really good metal, so we can still use it as an electrode. We put it in another water-based solution, and we coat it with a polymer electrolyte. That's this really thin layer. And then in the end, last step, we have a black ink. That is our cathode material with some conductive additives. We drop it on top of the sponge, it gets sucked in, we dry it, and then that's our 3D battery. So there are a couple of really important points here. The anode and cathode have to store lithium, and they have to be electrically conductive. This polymer electrolyte is really important. So you guys talked a little bit about electrolytes this morning. Did you talk about like what separates the two electrodes at all? Not really. very briefly. What's important about it is that it has to let ions go back and forth. Doesn't matter what kind of battery you're talking about, it has to let ions go back and forth. But it can't let electrical current go back and forth, otherwise you get a short. So current batteries have a porous separator, it's called. It gets soaked in this liquid electrolyte, and it mechanically keeps the anode and cathode separated. We can't really have that because of our architecture. So we had to come up with a way to basically conformally coat every nook and cranny with this polymer electrolyte. It has to be mechanically stable, but it has to be mechanically flexible, because remember I told you the electrodes expand and contract, and now ours are interdigitated, so they have to expand and contract kind of in concert with each other, and the polymer has to be flexible enough to accommodate that. It has to be stable at high temperature, because batteries get hot, especially if you charge or discharge them really fast. It has to let lithium ions go through, but it can't let electrons go through to high voltages. So normal lithium ion battery runs at about 3.6 volts. We've made our polymer stable up to about 8 volts because we figure there might be hot spots, especially where you see all these little curves. And we have to have a way to plate it so that it really does cover every piece of the battery, otherwise you get a short. So that's what I'm really going to spend the rest of the time talking about today, is the anode deposition and the polymer deposition. And I wanted to show you actual structures and data. Do you have a question? Yeah.
Those processes are aqueous?
Yeah, they are. Yep.
And at basically room temperature and pressure?
All they're in open tanks. We actually bought a set of tanks that's typically used in the semiconductor industry for their R&D line. So it's not the huge volume production, but they are 7-gallon tanks, and we do 6 at a time in racks, and they just go from a rinse process then into the first tank. The purple stuff I'm showing you, it takes us 60 seconds to plate. Take it out, put it in another rinse tank, put it in a polymer tank. That one I'll show you, that's a little trickier. We coat it, then we do a quick test to make sure it's perfect. If it's not perfect, we do a second coating. Then it goes in another rinse tank, and then it gets dried. So it's all...
You can recycle your material, you don't have to reject it.
That's right.
In semiconductor, you don't. I mean, you get one shot.
That's right. Okay, so I tried, I don't know anything about manufacturing. I'm a chemistry professor. I'm not a chemist in industry. But I know enough to know that if the characterization tools are slow, or if you have to check everything, it's not going to be cheap. So we tried to make every step its own test of how good it is, if that makes any sense at all. And I will show you the example of that with the polymer. And we tried to make it all kind of inline testing, and we tried to make it really quick tests where you could find a mistake over very large surface areas without having to look at every part of it. Yeah.
So at some point in there, then you connect a lead to the copper sponge into the outer surface of black.
Yeah, actually, what this picture is not showing you is we first put a contact here that we ultrasonically weld, and that is the contact that we use for all the plating, and then it stays as the contact at the end. And then at the very end, what we do is we put an aluminum mesh, and then we put the black ink stuff on top of that also, and it dries, and those are your 2 contacts. So we don't know that our contacts are in the perfect spots yet. So here I'm showing you in this little cartoon, one of them here and one up here. But the National Renewable Energy Lab has amazing equipment to test batteries, and they have a modeling group that will generate a computer structure of your battery and tell you what should happen over cycling. What they can do is actually cycle batteries basically and use thermal imaging, and they can see if there are any hot spots, and they can tell you, oh, your contacts aren't in the right place or they're not big enough. And so they are testing these for us to tell us if we have them in a good spot or not. So it is a single piece at the end, and that piece has a certain capacity, right? It has a certain amount of lithium in it that it can store. So if you want to build bigger capacity cells, you either start with a bigger piece of copper foam, and we get this stuff on big rolls, and we just cut out the size that we want. But in theory, you just would make a bigger battery, or you stack multiple layers, and that's how you build up bigger capacity. So the biggest ones we've ever made are, we package them as what are called pouch cells. They're just like what you have in your phone. They don't look as fancy because we do it by hand, but it's the same idea. And then to get bigger capacity, we've stacked 5 of them up, and we got a about a 0.5 amp hour battery. Your phone's a 1 amp hour battery, so we're about half of that so far. But we have been able to scale it up at least that far. Yeah?
What, I don't know if I'm asking this question right, but what is the native open circuit voltage for a single cell in your chemistry?
For us, it depends on the cathode material we use. So if we use lithium iron phosphate, which is what's typically found in like power tools, it's about 2.8 volts. If we don't use lithium cobalt oxide, we use a version of it that we make that has nickel and manganese in it to make it cheaper. So it's a lithium nickel manganese cobalt oxide. That one, we're at about 3.8 volts. And we could go higher, except our polymers are so slow at room temperature right now that we're working on trying to make that better before we go to higher voltage, but yeah. So it totally depends for us on the cathode material. Okay, these are great questions. So this is the anode we use, copper antimonide. So antimony is not probably something you would want to eat a lot of, but it's not, it's in the same family as arsenic, but it doesn't have the toxicity that arsenic has. This is the only part of the battery that you could probably argue is not truly non-toxic. But when it's in that compound, it's actually very safe. Now, graphite, again, if you think about mass, has a capacity of 372 milliamp hours per gram. Copper antimonide is lower than that, it's 290, and that's because antimony is such a heavy element. But if you look at it volumetrically, graphite's at about 800 milliamp hours per milliliter, and copper antimonide's at about 1900. So it stores a lot more per unit volume, and we chose that intentionally because right now, all lithium-ion batteries are limited by their cathode material. There are no cathode materials that have really good capacity. So we wanted to have a structure where a lot more of the volume could be used to store cathode material, so we wanted an anode that would take up less space. Now, the way this compound works is you start with copper antimonide, and this is how the kinds of chemists in my field look at structures. We pretend the atoms are spheres, and in this case, the antimony is gray and the copper is blue. When you charge it, you go through 2 intermediate phases, and you end up at Li3Sb, where now the light blue is the lithium, and again, the dark gray is the antimony. Most of these kinds of compounds have enormous volume expansions, and so they pulverize so fast that you can't really use them. There are companies now trying to use silicon instead of carbon, and it's a similar kind of idea. Silicon has a 300% volume expansion when you put lithium into it. Copper antimonide is only about 75%, so it's a lot lower. And the reason it works is because the antimony atoms basically don't move. They make kind of a skeleton. The lithium goes in, the copper comes out, and then it's reversible. When you take the lithium out, the copper goes back in, and that's how you cycle it. What's really important is that it lithiates about 50 millivolts more positive than the plating of lithium metal. So did you guys talk at all this morning about lithium fires or shorting? Anytime you see in the news a recall on batteries, like the big Sony recall, or fires like the FedEx plane that went down because of the lithium-ion battery pack, that's almost always because of lithium metal causing a short. So we can't have that in our battery because everything's too close. So we picked an anode that chemically can't plate lithium metal so that we could make it safer. The other good part about this material is that it is really conductive, so it dissipates heat really well. This is what it looks like when we coat it on our foam. So this is what the copper foam looks like. A lot of the stuff we make is smaller than the wavelength of visible light. So we use a lot of electron microscopes. This is a scanning electron microscope image. This is 1 millimeter here. So low magnification image, and you can see all these big holes. If you zoom in, you can see that everywhere there was an edge, the copper antimonide plated faster. And that's really normal for electroplating. And then the flatter parts, if you zoom in even further, you see these tiny little cubes everywhere. That's the copper antimonide. And again, you take this copper foam that looks just like the copper discs you guys have. We put it in a water-based solution, 60 seconds, and it comes out purple, and that's what that is. Now this part, my very first PhD student figured out. And I gave him this list that fortunately he just didn't know enough to know shouldn't have been possible. The list was, okay, you have to figure out how to electroplate this compound, and that had never been done. And it has to be out of water, and it has to be at room temperature, and you can't use anything toxic. So what he figured out was that he could do it, but only if he used citric acid, which is a really common food preservative. It's a special molecule that will bind to the two metals, shifts their electrochemistry basically right on top of each other. It does it in this really special way, and it is literally something you can eat a lot of, and it's so cheap. You can buy it for $10 per kilogram. And so he's the one who actually made this happen. So this was actually our first patent. It was based off of all of this work. So we can plate it. So how does it work? Now we're trying to build this crazy 3D battery, and each piece is new. So what's really important is that we study each piece separately so we understand how it works by itself, so that we make sure we're not studying too many variables at once. So what we did here is it's our anode, copper and timonite on our copper foam, but we used a normal separator. This is the flammable liquid solvent that's in your cell phone. We use the exact same one. This is the salt, LiPF6, that if it sees water, it makes HF acid, and that's what etches bones. So that's the bad part, but we used it for this test. Cathode is the commercially available cathode. We packaged it in the size and shape you would use for your phone, and we cycled it. Now, the key is that we cycled at a rate of 2C. So a C is fully charging and discharging your battery in 1 hour. Your cell phone's rated to work at about C divided by 3 or C divided by 5. And so we were going pretty fast. What's important here is that if we go out to, in this plot I'm showing you about 220 cycles, this is the percentage of capacity retained from where we started. There's a whole forming process I'm not going to talk about, but what's important is that if we look at voltage versus lithium metal as a function of time, every 20 cycles it doesn't change. All you need to get is that all these lines are the same. That to us is telling us our material's not degrading. It's acting exactly as it should. If we plot capacity retention, you see it's getting better over time. That's because we are roughening it every time it expands and contracts. And the rougher it gets, the more surface area it makes. And so it can go even faster. Now, batteries in the industry are rated to, your device is rated to tell you your battery's dead when it hits 80% capacity. So what you really want to know is how long does it take you to get to 80%. And in our case, we can go out to about 725 cycles. Now your cell phone, again, is rated to go about 300, 350 cycles, which really means that your battery will start giving you trouble every year. That could be designed to be better, but what they're hoping is you'll buy a new phone when that happens instead of just buy a new battery. So that battery, not a lot of work has been put into trying to make that last longer. But for cars, you can imagine that just is not financially reasonable to replace. So what we did is we took our battery again. Now it's not the full 3D battery, it's just our anode. We took a normal battery out of a BlackBerry actually, stripped its controls off and cycled it the same way. And what I'm showing you in black is our battery, and in red is the BlackBerry battery. The voltages were different because the cathode materials were different. But what you can see is that a commercial battery is just not meant to cycle that fast for that many times. So its capacity drops pretty dramatically, whereas ours is still better. So the whole point is just that this whole idea of making electrodes higher surface area works. And that part is pretty obvious in this field. That makes sense. But now what we wanted to do was put our polymer on top. Okay, so don't pay attention to the data yet. I'll just tell you again the thinking behind what we wanted to build. So this polymer electrolyte has to be ionically conductive, but electrically insulating. So we were thinking about what the best way was to do that, to coat this high surface area structure. And we decided that electroplating was still the best way, because as you make the polymer, it becomes insulating, and so then no more polymer can grow there. So polymer is only going to grow where there are patches, and if you keep cycling, then you will fill it everything, and you will end up with no defects anywhere. If there are defects, and these are typically called pinhole defects, then when you add the cathode in, you'll get a short. So the way that we monitor this is we apply a voltage. These are polymer electrolytes that we've developed because there really isn't anything in industry that can be made this way that works the way we need it to. If you look at the black line, this is the first pulse. So we measure current as a function of time, and now this is 0, and we're going to negative current because we're doing a reduction. So you see that the current starts high because a lot of polymer is being made. Then it drops pretty quickly and it evens out. Then we let it rest because these weird shapes, the liquid needs time to replenish itself in these odd shapes. So we turn the voltage off, we let everything rest, then we pulse again. So the second pulse is in red, and you see that the current started really low because most of that structure was covered already and no more polymer could grow there. So it can only grow where there are bare patches. It approaches zero pretty quickly. Then we let it rest, and then we do a third pulse, and the current's really low. So that tells us it's pretty good, but it doesn't tell us it's perfect. So this, I think, this is like one of the dumb things that I thought was my most clever idea ever, but if I had talked to an old electrochemist, they would have told me that this was an obvious thing to do, but it just had never been used in this field before. So here's the idea. You have this huge structure with all the surface area, and you cannot possibly check it all optically or with an electron microscope. So we wanted a way to know, is there one mistake just somewhere? We don't care where, we just want to know that it's there or not. So what we do is we take a small molecule that has really well-behaved electrochemistry. And when you scan in voltage and you measure current, you get this really typical shape that's often called a duck shape. So this experiment is called cyclic voltammetry. So on a plain electrode, this is what I mean by a duck shape. You see a peak here and it drops off. Then when you scan back, you should see the reverse of that. You see a peak here and it drops off. So if there's a pinhole defect anywhere and we put this molecule in solution, that molecule should be able to get through that hole and we will see that duck shape. If there is no mistake, we shouldn't see anything. So we call this redox shutoff. So this is what it looks like on bare copper antimonide. And then these flat lines are what it looks like on our polymer after we've made it, which means there are no mistakes. We have really sensitive equipment. Notice the size of this current. We can actually go down to nanoamps, so we can go to 10 to the minus ninth. And it's super quick. This test takes 30 seconds. If you see a pinhole anywhere, you just put it back in the solution with the monomer. You cycle one more time. The polymer will only grow where there's a mistake. Then you test it again and there's nothing there and you know that you're good. Now, this is what I mean by really sensitive. So now we're at microamps. After the first polymerization, you do see a tiny bit of this shape. It's not a real duck shape, so we know it's not a real pinhole defect, but what it means is that there is somewhere on this whole electrode that's thin enough that the polymer is diffusing through and could be a weak spot. So we polymerize again, one more cycle, and then it goes to zero. So this is also all done in water. It's all done out open in air, but it's it takes about 30 seconds for the test, and then if you see a mistake, you put it, you have to rinse, that's a minute. You put it back in the polymer solution, and then the next pulse is about 4-minute pulse, and then you just check it again. So this is how we know if a defect is there or not, and then also how we fix it.
How often do you get defects?
So now that we've optimized our polymer deposition, the guys are at about 1 out of every 45 has a defect. And if they see this flat line, when they put the full battery together, we're out of batches of 50, we're at 50 out of 50 that don't short. That doesn't mean they work great for other reasons, but it means they don't short. So now we can, so now it actually works. This idea actually works. Okay, so this is what it looks like, the full battery, and then I'll just answer questions. So this again is an SEM. What you're looking at is the full 3D battery. This is the aluminum mesh we added at the end to make contact at the top. And this is where you see a little bit of the copper foam. And all of this is that cathode ink that I didn't talk about at all, but it just looks like black ink that we dump on top. Then if we really zoom in, and I don't know if you guys can see this well enough far away, this is our cathode, and you can see the shapes of the particles. This is an older one. This is our polymer electrolyte, and you see it's about 4.5 microns thick. The newest ones we have now, we make it about 750 nanometers. And what happened here is we took the whole thing, we froze it in liquid nitrogen and cracked it so we could image it. And we noticed that when we froze it, the polymer pulled away. This is the copper antimonide here. This is the copper foam. Oh, thank you, Cynthia. Oh, that helps a lot, thank you. So this is the copper foam. This is the copper antimonide. Remember, it's thicker where you have an edge. and this is the polymer which pulled away. So now the way we make our polymers, it actually chemically bonds to the copper antimonide as it's growing so that you can't pull it away. We have gotten better at the deposition, so now it's thinner, 750 nanometers. But what this is really showing is that this cathode we designed so that it could wet really well to the polymer but not dissolve it so that it would get pulled in. And you can see that it does, it wet really well, it makes really good contact. So again, where we are today is the copper antimonide we know is really fast. It works, that part works really well. The slurry chemistry we've developed is also all water-based, and that's something that a lot of battery industry experts would tell you will never work, but it actually does work if you use new conductive additives. We can't use what they typically use, but we've designed some new ones that are safer and they're stable in water. But this polymer, the ionic conductivity is still too low. And so by too low, I mean it's like 100 times too low. So if we cycle it in a hot oven, it works better. For some applications, that could be really good, like these huge data storage centers that have banks and banks of hard drives. Those get really hot, and they do have power supplies that are meant as backups, and those are just batteries. Typically, the major failure of those kinds of batteries is the high temperature. Ours actually works better at that temperature, so that wouldn't be bad. But for a car, it wouldn't be good, because you can imagine in Colorado in the winter, the car would never start if you had this kind of a polymer. So we have some good chemical ways to try to reduce the temperature at which this will operate, and that's what my guys are working on now. But this is just to show you we actually do have a 3D battery. It doesn't short, and we can cycle it. Now, all of this was done, all of the initial work was done with graduate students and undergrads. So when I started here, my very first students had just finished their freshman year of college. So they didn't know a whole lot about electroplating or synthesis of materials, but they worked really hard. So those were the two that built my lab with me. What I'm showing you now is my current research group. Those are all graduate students you see in the picture. I have a mix of chemists and mechanical engineers in my group. And then the people that really did the copper antimonide have already graduated. So James Mosby was my first PhD student. He's the one who figured out the citric acid trick. And then my very first postdoc, Derek Johnson, worked on all the polymer stuff. And then I had a postdoc, Matt Rawls, who worked on the polymer stuff as well. My second grad student, Tim, also worked on the polymer stuff. So this has taken a lot of different people. The funding for this research originally came from the National Science Foundation. That was all the electroplating of copper antimonide. And now my startup company does cover some of it. And then the Semiconductor Research Corporation covers some of it. So I wanted to give you guys kind of the chemist perspective of how you would think about making the materials to put into a battery. And hopefully what I got across was that I think it's really important if you're going to build a new device to think about if it's ever produced on a mass scale, what will the impact on the environment be? If you're going to go through the trouble of coming up with the new chemistry anyway, you might as well try to think about that at the beginning rather than get all the way to the end and then have somebody else have to figure out how to fix it. So we have really, really tried to do that. I'm sure that when it gets scaled up, there will be other challenges. Certainly, again, I don't have a manufacturing background. I'm not a chemical engineer. But I think at least that having it all water-based does seem to be proving to be a good approach. Yeah?
I have two questions.
Sure.
If you throw your battery in the water, does it float?
No, it sinks.
It does.
Mm-hmm.
And then the second question is, can you grow your own structure instead of using a random foam orientation?
Oh, yeah.
Or could you precipitate out?
I'm not on my computer. So, the original idea was not the foam. It was nanowire arrays.
What's that?
I wish I were on my own computer. It's an array of tiny little nanowires. Same exact idea. You take your nanowires, these are copper antimonide. You plate the polymer around it in the cathode. But by small, I mean this dimension. We grow it anywhere from 100 nanometers to 45 nanometers. So the foam I showed you, if you take a square centimeter footprint of that foam, the total volume, or the total surface area is about 70 times higher than a piece of copper metal. This nanowire, array, it's 10,000 times higher than that. So you can fit, on the 45 nanometer diameter wires, you can fit about 10,000 in the width of a human hair. We grow ourselves, and the way we do it is we start with a piece of aluminum metal, and if you oxidize it in an acidic solution, it's called anodization, you grow this amazing, amazing structure that is holes that grow straight down, they don't ever intersect, and you control the diameter of them and their spacing. And this is kind of what they do, it's very, very similar to what they do for aluminum siding on a house. They put this thin aluminum oxide layer to make it really stable, particularly to rain. It's the same exact idea, except we grow it so that these holes grow in a certain way. And then it's exactly the same idea as making cupcakes versus making a sheet cake. You basically put metal on the bottom, and then when you plate this copper and timonite, it grows from the bottom up through this hole. Then you can selectively dissolve away the aluminum oxide, and you're left with these tiny little nanowires. And they are really fast. I mean, they are way faster than the copper foam that I showed you. The trick, though, is that it does take these two steps, the anodizing the aluminum and then plating, and then you do have to dissolve the aluminum oxide away. So when we were trying to design our polymers, we decided it was faster to use this copper foam as a tool. But then when we calculated what the performance of that foam should be, we realized that that probably was a good first battery. It's also cheaper. When we do the manufacturing cost calculations, these extra steps add quite a bit. So instead of 348, the nanowire battery is about 570. So it's a lot more expensive. The power density is way higher. I mean, 3 orders of magnitude higher. But it's just trickier to make. So in that case, we make all the structure ourselves. We don't.
So that'd be like generation 2.
Yeah, that's right.
After you're a millionaire.
Right. Actually, I never even thought of that part, actually. But yeah, that would be a pretty amazing. At that point, you would argue whether or not it's a real battery or whether it's a supercapacitor, because it's so fast.
That's
The-
size, would it be a capacitor?
That's right. The only way you could tell the difference is that ours can maintain a voltage for a long time because it's a battery, but supercapacitors can't do that.
Right.
But at that point, it gets in. That would be really cool to build
Yeah,
it all
it's-
kind of in one.
I know that that's actually a problem with some microelectronics is the
Yeah.
capacitance factor.
Yeah, that's right.
So that, and it's at that scale. Your polymer will work at that scale.
Right. It does. We know that part, actually. We already know that part. So, yeah.
So the copper foam is just like a scaffolding that you light stuff onto, it doesn't have anything to do with the battery?
It is also the current collector on the anode side. So it is the scaffold and it is the current collector. It's also a good heat sink. And our polymers, we know they're stable up to about 220 degrees Celsius, which is great. I mean, there are very few real batteries that ever get that hot, but we wanted to make sure they were flame retardant to get some of the safety built into it also. Yeah.
How is the foam formed, harvested, collected, and then
It's, so we buy it from a company. Originally, we were buying it from a company from the Netherlands. Now we're actually buying it from a company in China. And the way they make it is first they pressure extrude a molten polymer that when it cools, it gets all these air pockets in it. Then they use a chemical process to coat that with copper. And then they burn off all the polymer and you're left with the foam. That's why if you look at this picture, the foam is hollow. This is where the original polymer scaffold was. There are other ways to make it. You can make it where you electroplate copper and metal, but out of a solution that generates tons of hydrogen bubbles, and the bubbles will make the structure also. So we've thought about making it ourselves. Now it's faster just to buy it, and it comes in huge rolls, and we just cut it with scissors, or actually we use, paper cutter to cut it, and then my guys do the ultrasonic welding to put the tabs on, and then all the packaging we just use normal heat sealers and welders to make the outside packaging.
So you could lay or bend or roll or fold that,
That's
that
right.
medium into
Any
dimension
shape.
you want.
That's right. It's the only battery we know of that you could make into any shape you wanted.
So your glasses could be lined with
That's right.
copper foam battery.
That's right. So we started thinking about weird applications for that. Now there it's more complicated to think about where you put the contacts. But I mean, if you think about, there are things like your phone. Right now, smartphones and laptops are all built around the battery because the battery is so big and it doesn't give a lot of room for the circuit designers to build stuff around it. So you could imagine trying to build a battery, build all the circuitry that you wanted, and then make the battery fill in the space that is left behind.
Well, how strong, you talk about layers here too.
Yeah.
I was reading an article when I found a little announcement on the
Oh, yeah.
yours. But it also talked about using, for example, in a car, the body of the car, they're manufacturing material that will act as a battery.
Yeah.
Forming that around, so that now you're not talking about a battery in, you're talking about the whole thing.
Right. Now that one, for a car, that would be tricky because if you imagine what happens in an accident, I don't know that you could build packaging that would be mechanically stable enough. The way that now, like if you look in the Tesla Roadster, the battery is the entire trunk, and there's a pretty serious roll cage built around that battery. I mean, you guys know way more about that than I do, but the casing around the car batteries is pretty serious. So I don't know how you would do that with the outside, but you could. I mean, you could think about that.
So if your battery is bent or deformed, it shorts out, I guess?
If you do it enough times, it does. If you basically fracture the copper underneath, that's actually what breaks first. Then you don't have contact anymore.
What's the first fault in your battery? Is it the polymer?
It is the polymer, yeah. That's the hardest part of all of this. There have been a lot of other people that have tried to build 3D batteries, and all of them have failed because they all shorted. And the ways they made either polymer or inorganic electrolytes either they couldn't tell there was a mistake until they assembled the full thing, or they shorted over time. So that's why we really tried to think about a very crazy different way of doing it, because all the normal ways of doing this don't work. So there is no commercially available 3D battery yet.
So what's your polymer made out of now, and what are you testing or hoping to use?
We took some inspiration from flame retardant materials, and then we added backbone. So that's the backbone of the polymer. Then the side chains we actually took some from a compound that's a very common laxative for infants that has some good oxygen groups that are thought to help lithium ions move. And then we added in another monomer that is known to be mechanically very flexible. So we've mixed and matched a bunch of different things. They're all covalently bonded. They're all attached to the same polymer, but So I can't tell you it's good enough yet, but I can tell you so far it's all worked the way we thought it would. Yeah.
And so you dip it into this polymer, Now, you just hold it there for a while, or is it pressure pushed through?
Nope, we hold it there and then we apply a voltage. And when we apply that voltage, it makes the polymer form. And it's actually a two-step thing. We apply a voltage and then current gets transferred actually to another molecule in solution I haven't told you about. That one we call an initiator. That's what starts the polymerization. And then the polymer sticks to the surface as it's growing.
You mentioned 7-gallon.
Tanks.
That's not very big. That's like.
It's big enough to make about 10,000 a year.
And then, like, you just replenish the gunk?
So actually what we've been trying to do now is figure out a rational way to test the bath to figure out, because you only deplete, like for the copper and antimonide bath, you're only depleting copper and antimony. So what we're trying to figure out a good way to do is to monitor it so that we only have to add that chemical back in, but not replace the whole bath, so that we don't waste all the water and have to recycle all of that. That part's harder, but people do that in industry all the time. I know there are good ways to do that all the time. So for our method, we're just trying to figure out how to monitor it. But yeah.
What's the voltage that you apply for the electrolytic cleaning?
For the copper and antimonide, it's about 1.1 volts versus like a calomel electrode. They're tiny. I mean, it's a tiny voltage. And then for the polymer, it depends on which version we're playing with, but that's about 0.78 volts. It's a different bath, but.
I was thinking much higher.
Oh no, these are little. It's a plating, but it's just like jewelry.
Yeah.
That's exactly how jewelry's made. Yeah, yeah. So, I mean, at the beginning, people thought, oh, this is a great idea, but you'll never ever get it to work. But actually, that's why it's so important to be somewhere with great students, because the students have made the polymer part for a long time we could only make out of organic solvents. And I really wanted to try to avoid that because they have high vapor pressure and you have to work in a special kind of hood. And one of my grad students is the one who came up with a way to do that in water. And that was something that a good, experienced polymer person would have said that will never work. But he figured out how to make that happen. So it is actually all now out of water. It's all in a pretty open hood that you just go from bath to bath.
Where do we write our checks to invest?
That's right. No, let me make sure I can actually make the polymer work better first.
So where are your students? Are they doing postdoc work?
So let's go to the picture. Well, I'm pretty lucky. So Tim is now a senior scientist at the Toyota Research Institute in Ann Arbor, and he's actually working on magnesium batteries. Derek was my first postdoc. He actually stayed with the company, so he's now the director of engineering for the company. James stayed with the company for 3 years, and now he is at Ceramtech in Salt Lake City, Utah, doing corrosion electrochemistry. He's actually trying to figure out how to take animal waste products and generate feedstock from it. And then Matthew, who was my postdoc, who stayed with the company for quite a while, and he is still a consultant. Both of these guys, James and Matt, still consult for the company. He now is in South Denver working for a mining company, but he's trying to figure out how to make more environmentally friendly controlled explosives, which seems like an oxymoron, but it's not actually. That would have a huge impact on mining companies. And then my other students that worked on different kinds of projects are all over the place. So Shannon, for example, she's graduated. She worked on solar cells. Now she works at Argonne National Labs as a postdoc working on solar cells. So they've gone out kind of all over. They work really hard. The students here are amazing. And this summer, actually, for the first time, I have a high school student in my lab. He just got his driver's license last week. He's a homeschooled student, basically made it all the way through chemistry, and so he was sitting at home kind of bored. So we have him now making solar cells, making nanoparticles for solar cells. So, do you guys have any other questions at all? Cool. Well, thank you very much. Thanks, Cynthia, for the invitation.
Thank you.
I will